Okay, so it's 12, 15, 14, and we're doing Lewis dots. So you had 4 to draw when you walked in. You had CH4. We did this one together. You guys all did this pretty handily. So far, for the very simple ones we've been doing, we said the good first step is to draw the electron dot diagram for everything you're dealing with. And then for some of these, it's just like a jigsaw puzzle. Wow, okay, that's easy. I see how that fits. And this is definitely one of those because, you know, gee, you got 4 hydrogens and I got 4 spots where carbon can share. Oh yeah, okay. This is pretty darn easy. Oops. And I think you all successfully got to there. And then remember, we talked about this briefly. Whenever we've got 2 electrons that are being shared, we change that notation to a little line. So your final drawing is going to look like that. And that would be a perfectly acceptable drawing for methane cow fart CH4. Okay, good, great, easy. I think most of you at least got this one. So you maybe just forgot to convert your dots to lines, and that's fine. I didn't see anybody do this in this class, but I'll just mention it just in case. I had a few people in the other class who wanted to, you know, but the dot is on the top of the hydrogen. I must turn the hydrogen on its side to bond it over here. Please don't do that, because then it can be mistaken for an I, and we're not bonding iodine to the carbon right now. So, you know, you can keep them upright, so you're reading them all upright, because remember, those dots on the 4 sides are not reality. They're just a representation. We can move them wherever we want. Okay, good on that. And then, depending on what order you took these in, you had H2O, our old friend water. And again, we say, you know, good first step is to draw the dot diagrams. And this one is also kind of like a jigsaw puzzle. You know, we can look at this and go, oh, wow, well, those 2, whoops, I took that a step too fast. Those 2 can share, and those 2 can share. And then everybody's happy, and that converts out to, whoops, let me shrink. Okay, so that's what you end up with. Now, a quick word about the structure of water. We've talked about water as Mickey Mouse, and this is the way it very often gets drawn initially. Some of you had, and this is actually preferred, a different representation. Let me get that moved over. You had this. So here's the thing. Now, are those really different? Remember that this is a 2-dimensional representation of a 3-dimensional object. So we're going to talk a lot about shape and structure in 3 dimensions. We will be doing a lab when you get back from break where you will build models of all of these molecules. This is the one that is preferred because water is in reality what's called a bent molecule. So what's a hydrogen at the root? It's a little proton, a little naked proton. These hydrogens want to be as far apart from one another as possible. Well, let's talk about these guys for a second. What are they? So at their very simplest, what are they? They're electrons, and they're not being shared. These are unshared pairs of electrons. Well, those unshared pairs want to be far apart from one another too. And so water bends to keep the unshared pairs and the hydrogens at sort of opposite ends. We'll do more with that when we get into molecular geometry. But, you know, this, for reasons that you haven't yet talked about, is really the way that water is typically represented because it's a bent molecule. But because we're talking about a two-dimensional representation of a three-dimensional object, this other one, and you'll understand this better when you make the model of it, you'll see why, yeah, okay, you can't really say it's wrong. But this is the preferred one because it really clearly shows that water is bent, and water is bent. And there's our Mickey. You know, there's Mickey. Okay, so let's move on to the next one. We've got carbon tetrachloride. Carbon tetrachloride, it's affectionately called carbon tet very often. 1 carbon, 4 chlorine atoms, nasty in the short term and the long term, carcinogenic, causes birth defects, causes cancers, will kill you slow, will kill you fast. It's just nasty stuff. When I was in college, this is what we used in our kill jars for entomology. So you take a jar with a sponge in the bottom, you dump a little bit of carbon tet in, you soak that, actually it was plaster of Paris, soak the plaster with carbon tet, and then you just pop an insect in, screw the lid shut, and they die really fast. And then you pin them. So they don't use carbon tet anymore. I don't know what they do use. We were always told, yeah, just don't sniff too deeply. Okay. Take care with that stuff. There were several things we used which were illegal now. So again, good first step is plotting out the initial diagram of your stuff, whoops, of the molecules you're dealing with. And of course, chlorine's fun because it's a halogen. It's got 7. And this is another one. This is just like the methane. It's like a jigsaw puzzle. You can immediately see where these pieces fit. And you can almost immediately do this. And that's typically the initial step of drawing the structure there. And then we simplify that down to represent everything that's being shared with little lines. And we'll get all of our unshared pairs, and there are many here. Okay, and that's it. That's our structure. That's our Lewis structure for carbon tetrachloride. There's also a compound, carbon tetrafluoride. Guess what it looks like? That, but with fluorines and fluorides instead of chlorides. Okay, these are all good. So the other thing that I saw a couple people do in the other class, and I don't know if anybody else did it here, trying to put your lines in between things, so doing that, don't do that. That line is connecting them. Let it connect them. Okay? Don't turn your stuff on its head. Okay, so far so good, right? Fairly comfortable with these. These are pretty easy. These pretty much go with what we've done so far. SO2. So again, good first step, always draw what you're dealing with. And very often drawn like that. And it seems easy enough, then, to figure out how the first jigsaw piece is going to fit. And I'll copy this oxygen, so we have 2 oxygens that we're working with. Yeah, we can jigsaw that into place. We can sort of jigsaw that into place. Hey, that wasn't so hard. So we've got, whoops. It's like SOS, but backwards. There's a problem. There are actually a number of problems. So let me alert you to the first problem here. Anybody sensing any problems? Anyone sensing imminent danger? Okay, these things. So this is an unshared pair. That's fine. We can have unshared pairs. What we can never, ever, 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 never, never, ever, never have is a single electron. These guys don't travel alone. We can never have a single electron hanging out there someplace. They will always end up paired somehow. Something with a single electron is incredibly unstable. It doesn't happen. They operate in twosomes. So we can't have those. And right now we have two of them. This gets us to our next solution to a problem. So we'll go ahead and put the slide in. Multiple bonds! Yay! So what happens is those two electrons, in essence, remember how I said, don't get too attached to where the little dots are because we're going to shuffle them all over the place? Those both end up relocating and forming a double bond here. Double bond. You know what? Let's go back and check on something that we forgot to mention as we're going through our structures. Let's go through our checklist. So starting from here, whenever we think we're done drawing a Lewis structure, we want to go through a little checklist. Do we have all the atoms we need? Do we have 1 carbon, 4 hydrogens? Yes. Is everything happy as far as octet goes? And of course, remember, hydrogen's an exception. It just wants to share to get to 2. Carbon wants to share to get to 8. Each of these lines represents 2 electrons. So does carbon have 8 electrons? 1, 2, 3, 4, 5, 6, 7, 8. Yep, carbon's happy. Hydrogen wants to share to get to 2. This one's sharing 2, check. This one's sharing 2, check. This one's sharing 2, check. And check. Okay, everybody's happy. Water. Disregarding all of, well, here, we'll go on this one. So hydrogen, 2 and 2, check and check. Oxygen, 2, 4, 6, 8. Oxygen's happy. That structure's done. Fantastic. Carbon tetrachloride. The carbon feels like it is surrounded by 2, 4, 6, 8. It's happy. This chlorine, 2, 4, 6, 8. Happy. 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 Fantastic. Wonderful. Why am I bringing this up right now? Let's do our math. 2, 4, 6, 8. That oxygen's happy. 2, 4, 6. 2, 4, 6, 8, 10. We got problems. We got problems. So what ends up happening is we end up losing some electrons and they end up over here. Here's what we end up with. Oops. So let's go through that checklist again. 2, 4, 6, 8, happy. 2, 4, 6, 8, happy. 2, 4, 6, 8, happy. Everyone's good. Now, do we actually know that like this electron went here and this electron went there? Nope, we don't. Could it be that this electron went there and that electron went there and formed a double bond? Yeah, probably. And then this one goes over here. Yeah, don't let this look like the board after an NFL game where the crazy commentators are drawing circles and arrows and stuff all over the place. Nobody cares where they came from. Don't be married to where the dots are. I said we were going to build a beautiful Lego palace with a 2-year-old and then it was all going to get knocked down. Don't get attached to where those dots are. It doesn't matter. So, anybody have, let me get rid of my check marks, cut, cut, cut. Anybody have any other pressing questions about that? Anything bothering you? Nobody's bothered yet? You're all taking it on faith? Got a full stomach of hash browns and you just don't care anymore? So how do we know that the double bond goes here? Anybody wondering that? Well, that's something that's bothering you. Well, that leads us to our next question. Resonance. When something resonates, it vibrates at a given frequency. Resonance structures are something that is used when we have a molecule that could exist with something in more than one location. So let me back up and do a little bit of the history here. And let me draw the two possibilities for sulfur dioxide. And what we used to think, and by we I mean chemists, though I am really not a chemist, I'm a biologist, but chemists and physicists, because this is really down to like physical chemistry, physics and chemistry, used to think that in any molecule where there were two different ways for something to exist, like there are two different places the double bond could be, there are two different places where this unshared pair could be. In anything like that, they figured that it basically vibrated back and forth between the two. So, this is like somebody who's got two desks in chemistry and they alternate sitting in them every day. Okay, this is what was believed. And so that was represented like this. You draw them both, you bracket them both, and you put a double-headed arrow in between them. That's really important. This is how you show resonance. What you're saying is, it is in one of these two arrangements. So that should be a double-headed arrow. And these have to be bracketed. If you give me what you tell me is a resonance structure, but it's not bracketed, and it doesn't have double-headed arrows, it's wrong. It's not resonance. You have to show that. And what the resonance is intended to show is, it's going back and forth between these two states. What we have discovered in my lifetime, in the last 20 years actually, is it's more as if they are existing in something that is a hybrid between the two things. So it's almost like there's a bond and a half here, and there's a bond and a half here, and there's a half a pair here, and a half a pair there. It's kind of weird. It gets into some weird physical chemistry stuff, but you don't need to worry about that. What you need to know is how to show it. And if there are three possible places that a single bond can be, you have to show all three possibilities. It's not that terrible. Okay, so we're going to practice some of these together. Actually, you know what? So for how many of you, I'll ask this, are things like this sulfur dioxide where like, well, a couple electrons from here go there, and these go there, and that goes here? For how many of you are you like really frustrated? And I had the quote from this morning's class was, "This is making my OCD hurt." Like it's not neat, it's not predictable. Okay, good. Let's make it neat and predictable. Okay, so what I've given you is a handout called A Surefire Way to Draw Lewis Structures. And this was developed by a guy named Mr. Gooch. And Mr. Gooch is somebody who used to teach chemistry, and he took a few years off to be a stay-at-home parent. I'm not sure if he's back to teaching or not, but he developed a lot of good stuff, and I've stolen a lot of it. And this is a really nice, it's a nice layout because it puts it down to simple arithmetic. So and we'll use his example. We'll do CO2 together. Okay? CO2, good old carbon dioxide. And the first step for doing Lewis structures with Mr. Gooch is you count up how many valence electrons everything in there has. So for this, we're going to count and add, count valence electrons. How many valence electrons does carbon have? 4. And we have 1 carbon. How many valence electrons does oxygen have? 6. And we have 2 of them. So we end up with 4 and 12, 16 valence electrons. That's the total number of valence electrons that we're going into this with. So number 2 is what he calls counting up the octet electrons. This is really just counting up how many electrons everything wants. So if you have some exceptions like hydrogen or boron where they don't want to get to 8, you need to handle this differently. But carbon and oxygen each want 8 times 2 times 1. We get 24 what we call octet electrons. So if everybody was completely surrounded by 8 electrons, there would be 24 electrons. Now, the third step is to figure out how many they're going to share. So if everybody was happy and had 8, we'd have 24, but there are only 16 electrons between them. So we subtract the number of subtract the number of valence electrons from the number of octet electrons. So that's, 24 minus 16. There are 8 electrons that they're going to have to share if everybody's going to feel satisfied. Okay. Now, if you have a bond, a single bond, how many electrons are involved in a single bond? 2. So these are the number of shared electrons that we've just figured out. Shared electrons. Well, if we take the number of shared electrons and divide it by 2, guess what that tells us? We're going to have 4 bonds in this structure. So if we lay out our carbon and our oxygen, how many bonds are we going to put in there? 4. Well, we have 2 spaces to bond, so it looks like each of these is a double bond. You're almost done. The last step is figuring out how many unshared electrons there are. So, step 5. We said we had 16 electrons, and we're sharing 8. So here you just take the number of valence electrons minus shared electrons. In this case, it's 16 minus 8. And these get called lone pairs, unshared pairs. Any of those will work. So we have 8 electrons that are not shared. Well, let's count octets and see who's not satisfied. Carbon, 2, 4, 6, 8. Carbon's happy. You can't put anything else on carbon. These oxygens only feel like they've got 4 electrons. Well, 1, 2, 3, 4. 1, 2, 3, 4. Hey, guess what? We got CO2. It is relatively painless, honestly. Relatively painless. So here's the way this is going to work and the way the rest of the week is going to work. I added some homework problems, and they are Lewis structure stuff. They will be due Wednesday. So what's due so far is due Wednesday. Thursday and Friday we're going to do the holiday ornament lab. Those of you who are not here, I will figure out what I'm doing with you. I don't know yet. It's a challenge. When we come back from break, we will dive into the molecular geometry lab. On reconsideration, I want you to not turn in your labs from last week. I screwed up. I'm admitting this on tape. It's out there for the whole world to hear. I screwed up. I got all excited about the lab that you did, and we should have done that this week and talked about this last week, and I flip-flopped them, and oops. So there are a few more concepts I love that lab. It's like melting things. A few more concepts that I want you to have before you answer all the questions. So go ahead and hold on to that. You've had the concrete experience. We can abstract from it as we go. So now we're going to practice some Lewis structures together. Okay, so we're looking at number 39 together, and part A is too easy, part B is too easy. Let's do part C, shall we? So it says we have 1 nitrogen and 3 iodine. Now, one thing we haven't discussed yet that's pretty important. When we're building one of these structures, when we're in essence building a molecule, what goes in the middle? Here's a general rule of thumb. If you have 1 of something and 3 of something else, the 1 of something goes in the middle. In reality, here's the way it works. If you have carbon, carbon goes in the middle. If carbon is present, carbon is always central. Call it the central atom. In other cases, the thing that is less electronegative goes in the center. So whatever has the lowest electronegativity is going to go in the middle. Least electronegative, or carbon if you got it. And as a handy rule of thumb, in the compounds that we're dealing with, you can almost always figure it out because, like, oh, I've only got 1 nitrogen. That's probably in the middle. So, okay, let's start off with the Gooch method. So, first off, we're going to do what? Count valence electrons. Nitrogen has how many valence electrons? 5. We have 1 nitrogen. Iodine has how many valence electrons? It's a halogen. 7. And we have 3, so we have 21 and 5. We're looking for 26 valence electrons. Okay? Great. Now, in terms of octet, if everyone was completely happy, how many electrons would there be? Well, nitrogen wants 8. The iodines each want 8. So 8 times 4, 32. We'll go up to the top here. Step 3. How many do they have to share? So, the number of electrons everybody would like minus the valence. In other words, here, 32 minus 26. Okay. 6 shared electrons. Six shared electrons. So step 4, how many bonds? Well, that's shared electrons divided by 2. In other words, 6 divided by 2, there are 3 bonds in this structure. Okay, last thing we need to know. How many unshared pairs are there? So they have 26, and they're sharing 6. Valence shared. We have a lot of unshared electrons. 20 unshared, so 10 unshared pairs. Okay, let's go ahead and draw this. Well, if we just lay this out with 3 bonds, we get that, right? And we've got 3 bonds, but we know that we have 20 unshared pairs. And if we're going to start assigning unshared pairs, let's look at nitrogen first, our central atom. How many does it have? 6. Well, so if we do that, nitrogen's happy. Now, what do we know about the halogens coming in? They're surrounded. So if we go, so we got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. By golly. Looky there. Looky there. It's pretty easy. And I think that the Gooch math makes it easier because it tells you exactly how many bonds you're looking for, how many unshared pairs you're looking for. It was years of teaching Lewis structures before I found the Gooch method, and I have to say I think students are much less frustrated with having, you know, okay, I do this, then I do this, then I do this, I need this many bonds and this many unshared pairs. I can do this. You know, they will get more challenging, but none of these are charged, so we'll do that when we come back from break. Okay, I will turn you loose to work on 39, 41. For 48, for number 48, you're only doing the Lewis structure for now. Only doing, that's completely illegible. Only Lewis structure for now. Okay, that's it.